Welcome to the next video. If you haven't seen the previous one, it would help because we discussed the basics of biomolecules and the biochemistry we're going to be dealing with. Today we're going over some definitions that will be used and you should have a good conceptual knowledge of them. Okay, so the first word that we have even previously discussed is chiral, right? We talked about chiral structures, right, when we were discussing the 3D configuration of our amino acids or our biomolecules. So chiral actually comes from a Greek term, and it means hand. As we understood, this means that the mirror image of the object, when you superimpose it will not be superimposed, right? Because the relation between the two structures is the way your left hand is with your right? So the way your two hands are related with each other, if you keep them on top of each other, you would see they don't completely overlap. That is what we mean. So the asymmetry is what when you say chiral compound, you're referring to a compound that has an asymmetric center. So it can appear in two configurations, both not being superimposable to each other. Okay, and you have most commonly appearance of an asymmetric carbon atom, right, where it is covalently bonded to 4 different groups. And in that case, what happens is that it can occupy 2 different structures, right? 2 different tetrahedral structures, which would not be superimposable. That's what we mean here. The asymmetry. The next term is enantiomers. This is an optically active compound. Okay, this is going to rotate the plane. So when your polarized light interacts with it, it rotates that light. Either it will rotate it to the left or it will rotate it to the right. Okay, so a compound that is optically active and it rotates the plane of polarized light either left or right? So this is actually what we use D and L before, chemical names. This is what it refers to. And example can be, D glyceraldehyde or L glyceraldehyde, right? The term we discuss is isomers, which actually falls under both of these categories because it's relevant to both of them actually, right? We discussed what chiral means. So if you have a chiral compound, right, it has 2 different configurations. So these 2 are going to be mirror images of each other, right? Non-superimposable, but mirror images, right? So when you have 2 such compounds, you say that these are isomers of each other, and we also call them stereoisomers. We discussed this term as well. And optical or you can also call them optical isomers. Now, how is this relevant? We talked about how stereo means space. So when we're saying D and L configuration, that essentially just means that itself, that a compound will, let's say, be, if this is D and this is L, it's just going to have an inversion, right? It's like mirror images of each other. That's what we mean here. That's why they are also known as optical isomers, because they'll also be rotating the plane of polarized light opposite to each other. So there's that. And if you want to really make it clear, you can just remember this diagram, right? If this is yellow, this is and this is red, the opposite would be, first there's like a degree difference. Here is 109, and this will be this, and this is gonna be red. That's your understanding of what a mirror image is. Okay. The next term we're going to discuss is conformation. We've been saying this as well. Okay. So when we say conformation, we mean a configuration, right? And a spatial arrangement of what? When we're talking about a compound, it has its substituent groups, right? So the spatial arrangement of these groups, okay, and these can assume different positions without breaking, right? The same groups together can have different conformations, right? They'll be bonded in this way, but they can, in a 3D space, there is numerous kind of positioning, any angle, that can change, it can take place, and it's not going to break the bond, right? You can call that the freedom of rotation, right? Freedom of bond rotation. You must have seen those 3D models that come when you're studying chemistry. You must have seen them in a lot of videos even, right? They're free to move, they have hinges. So just like that, you can imagine the conformation. So the example we've already discussed, D or L conformation, right? So a spatial arrangement of organic molecule that is confirmed by the presence of either the double bonds, about which there is no freedom of rotation, and also chiral centers around which the subsequent groups are arranged in specific sequence. So what we mean here is that this conformation basically means this arrangement and how we understand it, right? What we look at it, we look at any double bonds, okay? Since double bonds cannot, there is no freedom of rotation when you have double bonds, okay? There are some double bonds around which you'll have no freedom of rotation. And then there are chiral centers, and you have your groups arranged in a specific sequence, right? If there are chiral compounds around these centers, you'll have it in a very specific arrangement. So you recognize that, and that's what we refer to as conformation, right? How do you understand conformation of a compound? You look at these parts, and you have a term under here which we know as configurational isomers, okay? And an example of this would be cis and trans conformations. Okay, so the thing here about them is that since their configuration has to be set in a way, some of these can actually not be interconverted into each other. Okay, these have double bonds, right? So these cannot be interconverted without breaking one or more covalent bonds. Okay, so we've understood what conformation is, right? The spatial arrangement. Okay, conformation is something that is just an arrangement and there is a freedom of bond rotation. Okay, and D and L conformation would fall under this. Configuration is the spatial arrangement of a molecule, and this is more like, you could say, indexing, right? What is the configuration of this? Conformation is more like what's the shape it's taking. Configuration is exact, and you understand it by the 2 points I mentioned. And here we have configurational isomers, right? And these isomers have different configurations in a way that they can actually not be interconverted into each other without breaking one or more covalent bonds. The example I mentioned can also have their examples, being cis would be malic acid, it's a cis isomer, and trans isomer would be fumaric acid. Okay, so if you look at the structure, it's something like and fumaric is, there's like a flip here at one end. So for this to interconvert into each other, into it would have to break a bond. Okay, so your understanding should be, and why is this called cis? When you have your groups of importance, your priority groups, they're on the same side, then you call them as cis, or you can say identical, right? You can say identical or on the same side. You know what cis means? It's being similar, right? While trans is when you have your identical groups on the other sides. So that way you can remember which one has a cis uh, structure and which conformation is the trans conformation. Alright, so the clear difference is that we also have conformational isomers where there would be no bond breaking. Why? Because there is freedom of rotation, because the rotation that is actually happening happens at the and unless there's a ring or a double bond, you wouldn't really uh, have an issue. No bond would have to be broken because these are free bonds, while here you have double bonds, or there could be a ring where you'd have to break a bond, right? You could have to, double bonds have pi bonds, so you'd have to break that. Or if there's a ring, so in order to reform, in order to rotation to happen, you have to break that bond. Okay, so this is configurational. So cis trans conformations are actually configurational isomers, they're not conformational, for this reason that they'd have to break a bond in order to interchange. So what is the significance of all of this? What are the biochemical consequences? of having molecules in different configurations. So also note that when these are in such different positions, these actually have very different chemical properties as well. They're not merely different versions of each other, they are completely different compounds, right? You can see from the name itself, we're not calling them D or L or version 1, version 2. These are completely different names. So biochemical consequences of having these molecules in different configurations. We're aware about how ligands and receptors react, right? If you're not familiar with the background, you should know that a receptor recognizes a ligand. You can remember this as like an antibody or an antigen reaction, something that recognizes a particular bond, a particular spot, and fits into it. It can be a catalyst, it can be an enzyme, right? And this is so much significance in the mechanism of any biochemical pathway, right? So all the regulation is all the importance of the regulation is held in its hands. So you have ligands and receptors. Okay, we studied in the previous video that these are stereospecific, right? If this is a different version, or if this ligand instead of being this has a different structure, it won't be recognized, right? So if you have a molecule that is the same composition, you understand composition, right? Composition is a very simple term. Composition of a painting, composition of a room. What makes it up? Okay, what are the things making it up? That's all that composition is, right? So the same composition can have different configurations. You understand that? If I have an apple, I have a mango, I have a pencil. This can be one configuration, and this could be other, right? So that's to say that so the same composition can have different configuration, and that would bind to different receptors, right? So this same you could say made of same things but having different structure, could actually uh, so this would respond to this but not to this, and this would to this and not to that. So this overall is increasing your functional diversity, right? Yeah, different is binding to different receptors specifically, so it's more useful. You have more diversity, you can regulate pathways more closely, right? And an example of this is R carbone and S carbone having different configurations, and therefore they react, or they have different receptors that they can bind to. Okay, and these are actually present, these are actually have their functioning in our nose, so they bind to different receptors in our nose. Okay, and when this it gives something specificity, right? So when this one binds to a specific receptor, you get a sensation of a spearmint. Must have had those mints, right? So it's thanks to this. This is the ligand that binds to a specific receptor and gives us this smell. Okay, while if this one binds, you get like a pungent smell, very if you have biryani, or if you're having a particular spice, there's this pungent smell. So that's your But mention smell, it could be of a caraway. Now what a caraway is? It's like a spice. So yeah, that's the point. Having just different configuration but same composition, you get the specific sense of smell. Alright, so in confirmations you can actually also have examples. We have examples for configuration, cis and trans. For confirmation we have examples of eclipsed and staggered configurations. Okay, so these confirmations is basically that this is eclipsed looks a certain way, and it's usually one of them is stable and the other is rather unstable, right? So it's just the same again composition and different confirmation, and but the configuration remains the same. It doesn't really have, it's just rotated a different way. Okay, and it allows free rotation and it can interchange quite easily. And staggered is actually stable, eclipse is unstable, and you can, an example would be of ethane, right? If you see ethane, there's this would be your staggered one, right? Let me draw that more clearly. Okay, these are all H bonds. It's cyclic structure, and it can interchange with its eclipsed form. Now eclipsed would be more spread out, looks like an eclipse. Okay, so it's more stable because its energy that it needs to maintain that structure is less. It's actually 0 kcal per molecule, and this one is 2.9 kcal per molecule. So this is more stable. This is your ethane. Okay, two different conformations, interchangeable, right? And we have other compounds we can get into. We have furan, furanose, pyrene, and a good we'll actually cover that in another video, something called Haworth formulas, where we use it to convert a Fisher structure into Haworth, right? And you form the ring version of monosaccharides, right? By using, there's some bond rotations you make happen, and then you can form the ring structure of monosaccharides. We'll cover that in another video. It's also a very fun exercise to do. And if you want to know about them in brief, furan is a heterocyclic organic compound, and furanose is a simple sugar. It has a 5-membered furan based ring. Okay, and its ring actually consists of 4 carbon atoms and 1 oxygen atom, which is actually quite prevalent in biomolecules. And pyrene is a 6-membered heterocyclic ring. It has 5 carbons and 1 oxygen atom, and it has 2 double bonds. What does heterocyclic mean? We know what hetero means. It means different, right? So the ring structure actually, we know that commonly we have carbon and oxygen. So heterocyclic ones have an additional atom that isn't carbon. Okay, so it would, for example, furan is C4H40, right? So it's again 5-membered and it has an oxygen in it. So that's what we mean by heterocyclic. And heterocyclic can be 3-membered, meaning, and 5-membered and 6-membered, that you understand, right? And yeah, for now this much is a very clear understanding, I hope. Let's do the last two terms, which is racemic mixture. Okay, so what is a racemic mixture? A mixture that has equal amounts of two isomers of a chiral molecule. Simple, understood, right? A molecule that is chiral means it will have different conformations that do not superimpose on each other. They are mirror images of each other, such as L and D conformations. Okay, so to make a mixture, a racemic mixture, what would you do? Equal concentration of this and equal concentration of this, and you mix it up. So these two isomers, right, would be in equal amounts. Okay, so a DL mixture, okay, you call this a DL mixture, L and D. Okay, and the last term is hemi-acetyl or hemi-kettle. Okay, so this is a reaction. It's a general reaction that happens when you take a carbonyl group, right, like an aldehyde or a ketone, and the reaction happens with an alcohol form, and this forms a hemi-acetyl or hemi-kettle, right? So when it reacts with an aldehyde, it's hemi-acetyl, or it's hemi-kettle when it reacts with a ketone, right? A carbonyl group reaction with an alcohol would form a hemi-acetyl or hemi-kettle, right? What does hemi mean? Hemi is in general used hemisphere, right? Hemi means half. Okay, so when you're saying hemi-acetyl, you mean that aldehyde is reacting with one equivalent of alcohol, right? So that's hemi-acetyl. It's half of that aldehyde, it's half of that alcohol. And if it were to react again with another alcohol, it would become acetyl. It wouldn't be half of it anymore, right? And hemi-kettle again, ketone reacting with alcohol, half of each, right? Thank you for today's video. We're covering these. There are some more terms which will then fall under your specific lipids or carbohydrates. So we'll get into that when we get there, and we'll also cover Fisher projections when we get to carbohydrates, so that everything is in an ordered manner. We won't mix it up. And thank you. Be there for the next video.